Thank you. I'll begin with a word of prayer. Dear Heavenly Father, we thank you for this day. Again, Lord, I thank you for this class. I just ask you to bless our work today. And just thank you for the break, which is about to start. Help us to get rested up for the break, Lord. In your name I pray. Amen. All right, so got to the first isomorphism theorem last time. I haven't proved it yet. But before I prove it, or even state it, I just want to try to talk about it intuitively for a bit. So, what's the deal with a homomorphism? If this is lecture 15, right? I don't have a title yet, but I suppose I'm hoping we eventually talk about some things in chapter 8 today. We'll see. In any event, so if we have a homomorphism, phi, say from G1 to G2, right? And the kernel. Last time we proved that the kernel of phi is what? It's a normal subgroup, right, of G1. This we argued last class. And so what that means, right, is that G1 mod the kernel is a well-defined factor group. All right. Just a brief recap of what we did. A little bit more than that, of course, but now, what makes a homomorphism of a group really different than some other things is, let me just, I use this example because it's easy, but if you look at f of x equals to x squared, right? What kind of mapping is this? Right? Well, it's not one-to-one, right? So like from the reals to the reals, let's say. So here, it's not one-to-one, right? Because you know that f of plus or minus a is equal to plus or minus a quantity squared, which of course is just a squared, right? So if a is non-zero, both a and minus a both map to the same point, right? So this is what's known as, well, so let's say for a not equal to 0, we have f is a 2 to 1 map, right? It takes 2 points in the domain and squishes them to 1 point in the range. However, that's not universally the case, right? There's an exception to this rule. Except for what? 0 maps to 0, right? And so the mapping is in some sense one-to-one at that point, although that's not a concept we usually define. But you see what I'm saying? Like that point maps to 0. There's no other point that maps to 0. It's one-to-one in that sense. Well, a homomorphism, right? G1 is what? So if I drew a picture of G1, right? Like this, then something in here, right, is the kernel of phi, right? And then something else in here might be like a times the kernel of phi, right? Something else might be something like b times the kernel of phi, right? I mean, the domain of G1 is parsed into cosets of the kernel, right? And these are not of distinct, I mean, these are the same size, right? We proved that about cosets. Cosets all have the same size. So, maybe this over here is something like AB times the kernel, just to make a silly example. And the thing is, if that's the case, then if you want to draw a picture, the homomorphism phi just maps to, this little thing with what? The kernel phi. So it maps to, let's say, E, phi of A, phi of B, and phi of AB, whatever that is, that's it. If there are just 4 cosets, then it would look something like that, right? The point is that I'm trying to get to here is that phi is a kernel phi to 1 map. Right. And, well, technically I should put phi bar here, because what I've done is I have assumed that the mapping was a surjection. Right? There could be, in principle, G2 could have lots of other stuff that phi doesn't hit. Right? So if I'm assuming it hits everything, then phi is a surjection. So just to, allow for the possibility is not, I put a bar over it. Let's see here. So how does this work? So like, how's it go? A kernel phi times B kernel phi, how's that work? That's a coset space, right? How do we multiply those? AB kernel phi, yeah. So you see what you have, right? Is you have phi bar of A kernel phi times B kernel phi. I should have given kernel phi a name like N or something. So much kernel phi writing. Sorry about that. Now this would be equal to what? Well, it's equal to phi of AB, right? That's what it maps to, and this, of course, since phi is a homomorphism, is phi of A times phi of B. Which is what? Which is, by the way, phi bar of kernel. It's phi bar of A kernel phi times phi bar of B kernel phi. This phi bar map I'm describing maps from the factor group, right? So this picture is really a picture of G1 mod the kernel, right? Because I'm thinking of those 4 different sets in there as the elements of the factor group, and you can see if you define this phi bar, right, as I'm describing, from G mod the kernel of phi over to the image of phi, right? Phi of G1, phi of G1. So then this mapping I'm describing should be, well, it's definitely a homomorphism, right? Because of things like this, because of how we defined the coset in terms of the kernel and the fact that phi is a homomorphism. And what's the kernel of phi bar? Oh. Kind of blow your mind a little bit. What is this phi bar map to 0? The kernel of phi, right? Which is what? In the factor group, that's exactly the identity, right? So what you've just told me is that this phi bar has the kernel, which is the identity, which happens to be the kernel of phi in the factor group, which is to say that phi bar is an isomorphism. That is the first isomorphism theorem. Let me state it carefully and prove it. So this is just a heuristic, My brother claims this discussion helps students understand. I'm not entirely convinced. I'm sure he does it better. I've done something wrong here. You guys don't look convinced. I don't know. Let's see here. Yes, here we go. So here's the theorem. If we have a homomorphism, phi, from G1 to G2, all right, then phi bar from G1 mod the kernel of phi to phi of G2, which is that's the image of phi, right? Phi of G1 rather, sorry, is an isomorphism where we define, how do we define it? We define phi bar as follows. Phi bar of, let's see, what's a typical thing in here? It'd be like x times the kernel of phi, right? That's a typical element in this factor group. And what's its value? What's the, how do we define phi bar of x times the kernel of phi? Exactly. Yeah, what else can we do, right? So that's exactly it. Phi acting on x. And we do that for each, x kernel phi in G mod the kernel of phi. Of course, G1 mod the kernel of phi. Of course, I'm saying that because it just makes me happy to define a function in terms of all of the points in its domain. But of course, logically, this could be replaced with what? What's another way to say the same thing? X an element of what? Just G1, right? That's entirely equivalent. Okay. Okay, so that's the first isomorphism theorem. So let's prove it. So what is there to prove? So first of all, we should show that phi bar, right, is a what? A homomorphism. Well, first of all, phi bar is well defined, right? Phi bar from G1 to the kernel of phi to phi of G1 with phi bar of x kernel phi equal to phi of x. Well, this is clearly an element of phi of G1, right? As x is an element of G1. So the mapping's into, right? Its codomain isn't crazy, right? Essentially by construction, the codomain makes sense. And is it well defined? See, that's something that's not obvious. We're defining a function on a coset space, right? To show it's well defined, I should show that the function's single valued. So what should I do to prove this, that it's single valued, that it's actually a function? Suppose, right, that x kernel phi is equal to y kernel phi. What's that mean? That means that xy inverse is an element of the kernel phi, right? Or simply that phi of xy inverse is equal to the identity. If you like, it's the identity in 2. Would you like me to distinguish? I can. It's the identity in the second group. So I'm supposing I have two different representatives for the kernel cosets, right? Now consider then, if we take phi bar, right, of, oh, I'm sorry, I should probably just, what's this mean? Let me get a little bit more out of this. This means what? Anyway, so this means phi of x times phi of y inverse is equal to E2, or phi of x is equal to phi of y, right? Hence what? Phi of x kernel phi is equal to phi of x, which is equal to phi of y, which is equal to phi bar of y kernel phi. Therefore, phi bar is single valued. Which is important, right? You guys remember test 1 in Sprano's Calculus 1? What was the first question on the test? Definition of a function. Still matters. Mine too? Oh, I'm such a follower. Oh, man. I'm kind of sad for that. That's not from me. I just, man, I'm disappointed in myself. That's Dr. Sprano's question. I shouldn't use that one. Oh, on. It really? You put it test 1, test 1, test 2, test 3? Yeah, I think my patience for that question wanes after the first test, usually. Okay, so, oh, great. So we've shown that, now we've shown that phi bar is actually a function, all right? That's actually important. Now we need to show it's an isomorphism, right? So first of all, let's start with showing that it's a homomorphism. That's pretty easy. Notice if we have phi bar of x kernel phi, man, I'm getting tired of writing. Can we put? I've had enough of this. Kernel phi equals to k. All right, xk, yk, right, is equal to, of course, phi bar of xyk by the definition of the coset multiplication, and which we proved made sense in previous lectures. So that's phi of xy, right? By the homomorphism property of phi, because we're assuming phi is a homomorphism itself, right? That's phi of x times phi of y, which, by the way, is phi bar of xk times phi bar of yk. And there you have it. Thus, phi bar is homomorphism. Is it a surjection? Let's see, you pick anything you like. Let's pick phi of x, which is an element of phi of G1, right? That's a typical element in the image of G1 under phi, in the range of the homomorphism, right? And how do you map to that? Phi bar of x. Oh, I'm an idiot. Just a second. Oh, yeah. Yeah, sorry. I'm an idiot. So phi bar of xk is phi of x, right? So we map to it, right? Thus, phi bar is surjection. It's kind of unexciting, but there it is. And finally, to show it's an injection, we have it as a homomorphism, right? So all we got to do is calculate the kernel of phi bar. The kernel of phi bar is equal to xk in the factor group, G1 by k, such that phi bar of xk is equal to E2, which is what? Xk such that phi of x is equal to E2. In other words, it's the kernel of phi. It's k. In short, it's the identity in the factor group. It's the identity in the domain of phi bar, which by our earlier theorem about injective homomorphisms being captured by trivial kernels, well, that shows you that phi bar is injective. Thus, phi bar is isomorphism. There you go. That is the first isomorphism theorem. I don't know, was this picture helpful that we did? It was? Okay. It's not my picture. You can disagree. All you do is hurt my brother's feelings. I don't care. He's not here. I won't tell him. Oh, I might tell him. Let's see here. It's probably worthwhile. It's probably worthwhile for me to take a second to try to explain how the mapping phi bar relates to the mapping phi directly. So like, so here's just some context, let's say. So we have phi, which is a mapping from G1 to G2, right? How do I get from G1 to G1 mod the kernel? I can use the fundamental homomorphism we talked about last time, right? So the fundamental homomorphism will get me from G1 to G1 mod the kernel, right? Again, K equals kernel phi. Okay. Now, how do I get from G2 to the image of phi of G1? Well, let's see here how to do that. Oh man, I don't know. See, it's like I'm just cutting off part of the. See, I forgot my picture. I can say this much: the image of G1 is like a subset of G2, right? Generally speaking. In fact, it's a subgroup for what it's worth. There's something called the inclusion map. So like this, I maps from, say, A to X, where X is if A is a subset of X, then the definition of the inclusion, usually there's no dot on the top. This is actually a iota, or like IOTA. And so the way it works is just this. Iota of A is equal to A for all A and A. It's a very boring map. It gives you a mapping from a subset to a superset, just like that. So, I can put phi of G1, I can include that into G2 like that with this map, right? And then, basically the phi bar is here, right? You've got G1 mod the kernel here, and to get from there to G1, what do you use? You use the fundamental homomorphism. So in total, this thing is our original phi. So that's the relation between phi bar and phi. It's like phi is equal to iota composed with phi bar composed with pi. This is how the induced isomorphism is related to the original homomorphism. It involves an inclusion and this fundamental homomorphism map. But anyway, let me stop talking about this stuff for now. Let's look at applications to the theorem. It's probably better for me to do that. If I can find my notes. Oh, I hid them in plain sight as usual. Any questions about the proof before I go on? Any questions about my iotas? Yeah?
Should the phi of G1 in the middle there, should that be phi bar?
No.
Because over there you've got phi is iota, phi bar, pi.
Well, the phi bar goes from the quotient, the factor group by the kernel, to the image of G1 under phi.
Right.
So I start with a point here, right? Like G. Then like pi of G, where is that? Well, pi of G is an element of G mod G1 mod the kernel, right? And then I take phi bar of pi of G. That gives me an element of phi of G1. And then this is the stupid step. I take iota of phi bar. I'm saying that wrong. My apologies to all my Greek friends. Let's see here is an element of G2. The last step is very stupid. The point here is there's a larger point to be had here. You can take any function you like, all right? Any function you like. Think about this. If I have a function f, and let me draw a picture. So here's A, Here's B. I have a function f from here to here. If you want to take that function and replace it with a bijection, you can do it. What you do is you notice that there's something called the fiber equivalence. The domain is parsed into disjoint things. These are the fibers of f. In other words, those are the inverse images of points over here. Here's P. One of these would be f inverse of the singleton P. You can prove that the fibers partition the domain. They're disjoint, right? Because if the function's single valued, it just maps to one point. So everything that maps to P is in that fiber. All right? So this gives you a partition of the domain. And then, okay, so the function just maps onto some particular subset of B, right? Like this, let's say. That's f of A, right? And so what you can do is just take a cross-section. You take a cross-section of the domain, which means that you pick one point from each fiber, like that. And you just say, each one of those gets sent to the corresponding point over there. And it gives you this f bar from, let's say, the I need a good notation for this. I don't know, like f bar is basically equal to, well, it's not equal to that either, though. It's it's restricted to the cross section. We call it the cross section C. You restrict to the cross section and replace B with f of A. That's the inclusion step. You're changing the codomain to be the range. So these two things can be done for any function, and any function can be turned into a bijection by this chicanery. You're like, well, how can you pick one thing and each thing in the partition, you know? Axiom of choice. Okay. So there's our first use of the axiom of choice. So hope you're happy. I know I am. All right, I digress slightly. Not much, though. So some examples. Start out with something easy. Well, relatively easy. If I look at the determinant, right? That's a mapping from G, L, and R to the what? Non-zero reals. If I look at the, I mean, you could look at other fields, but I'll keep it real for a second here. Is this a homomorphism? Yes, homomorphism. What's its kernel? In other words, what are the set of matrices which map to 1? We talked about this before. The kernel is SL and R, right? A such that the determinant of A is 1. Last time we were here, we didn't know quite as much as we do now. Now we get a little bit more. We get to say that GLN, R mod SLN, R is isomorphic, right? To what? The image of the determinant, right? Is the determinant onto? Can you find a matrix which gives you any non-zero number you like as a determinant? Can you prove the determinant's surjective? How would you do it? Here's how I do it. The determinant of C, 1, 1, 1, is C. For any C in there. So there you go. That matrix gives you determinant C for any non-zero C. That's in GLN. So the determinant's a surjection, which means that this is actually isomorphic to that by the first isomorphism theorem. Okay? So there's an example of it. Let's look at another example. This one you guys might like more. Maybe. Maybe. We shall see. Every cyclic group is isomorphic to either Z or Zn. Let's prove it. So suppose you've got G, which is cyclic, right? So there's two subcases here. Subcase 1 is that the order of A is equal to infinity, right? Then you can define phi of M equal to A to the M, right? Notice this mapping, right, is a homomorphism from where? So homomorphism from the integers to G. Do you need me to write down why it's in a homomorphism, or can you prove it? Phi of M plus K is A to the M plus K is A to the M is A to the K is equal to phi of M times phi of K. There you go, it's a homomorphism. What's its kernel? From our previous work on cyclic groups, we know this is what? If it has infinite order, what's the only possibility here? By definition of infinite order, this has to be just the set containing 0, right? So here we get that Z mod 0, which is a really dumb quotient, but there it is isomorphic to G. Because it's also clear that this is a surjection, right? You give me A to the M, I get to it by mapping M. That works for any M. I mean A to the M. Now, of course, Z mod 0 is isomorphic to what? Just Z, right? Could you prove that? How would you prove such a thing? Z mod 0 is isomorphic to Z. How would we prove that? I mean, there are various ways. It's really not that interesting. What is this set? This is like X plus the set containing 0 such that X is an element of Z. All right, now that I've made this explicit, this is the factor group with respect to the additive coset of 0 over the integers, right? Can you tell me the isomorphism of this set? I mean, psi of X plus 0 equals to what? X, right? And you can prove that this is a bijective homomorphism, right? There's one way you could show they're isomorphic. And there's probably other lazier ways to do it, but it is in fact true. If you take a group, mod the identity in the group, you get it's isomorphic to the group again. It's very silly. What you're doing is you're taking cosets, you're making little one-point cosets. Basically, you're replacing your set with a set of singletons. It's like you're just putting little curly brackets around everything in your set and calling it a new set. And then you're multiplying it by the same rule, but now for the sets instead of the elements. It's very annoying. But now we did it, so we know it. This is just as true for Z as it is for G or something else. I mean, it's generically true that G mod the identity is isomorphic to G, all right? Something you should know about. Now, what's the other case here for cyclic groups? The other case would be that the order of A is equal to, say, n, right? And so we could say phi of, let's say, I'm going to be really explicit here for just a second. The coset containing k is equal to, a to the k. And here, this is my notation for k plus n z. So in so doing, I've defined a mapping phi from z mod n, right, to g, I suppose. Oh, well, that's not what I wanted to do, is it? Oh man, I took all the fun out of it. No. This is no good. This is no good. I mean, you could do this, but this is not the way to do it. It's really not. That's a bad choice. We don't really get to apply the first isomorphism theorem if I do it that way. It's much more interesting if I do it this way. We say phi, a mapping from z to g, how we're going to define it. Phi of m equals to a to the m, right? Where we have a to the n is equal to e, right? The order of a is equal to n. We're assuming that we're working with a cyclic group of order n, all right? Generated by a. All right. Is this a homomorphism? Yes, it is. Is it surjective? Yes, that's pretty clear. Okay, so what's its kernel? So that would be m and z, right? Such that a to the m is equal to e, right? But how can you get, that means that m is a multiple of n, right? By our work on cyclic groups before, that just implies that m, well, more to the point, n has to divide m, right? M is a multiple of n. So what is that set? This is exactly multiples, this is nz, is what we call it. Because m has to be like some multiple of n. All right? Any multiple of n, when you feed it to phi, it maps you to the identity. Okay, so what's the first isomorphism theorem say then? It says phi bar, right, from z mod nz is giving you an isomorphism to g. Or more to the point, z mod nz is isomorphic to g. You could do this same thing, right, to the explicit case that g is equal to zn, and come to the realization that, of course, is, a side benefit of this is just that our z sub n is really just the quotient. It's the factor group of z by nz as well. To make it a little less abstract, that particular cyclic group of order n, the integers under modular arithmetic, is, in fact, it's not just isomorphic to z mod nz, it is z mod nz, in fact. That's perhaps a distinction, right? I do mean equality here, whereas that's just isomorphism. Okay. Another good example of the first isomorphism theorem at play is, there's so many examples. Where did I put my, oh, yeah. I guess we don't need this anymore. Three. If we look at phi going from the reals to the non-zero complex numbers, and we define phi of theta equal to cosine theta plus I sine theta. This is an interesting mapping. It's an exercise in trigonometry, but you can show that phi of theta plus beta is equal to phi of theta times phi of beta. This is not entirely obvious. You have to use the adding angles formulas for sine and cosine to derive that. All right? That was almost on your last test. First test. But then I got rid of it. But I like that problem. Anyway, because I think students are supposed to know adding angles formulas for sine and cosine. That's a world in which I live. It may not be a world in which you live, but you should be warned. That is one of those misconceptions I harbor about students and things they know. I digress. So, you can also show that the kernel of phi, right, is going to be basically theta in the reals such that what? You need cosine of theta equals to 0, and you need sine of theta equals to 0, right? So cosine of theta, oh, I'm sorry, I'm an idiot. Kernel of phi should be theta in the reals such that this is equal to what? Not 0, but what? This is the multiplicative group of complex numbers, so the identity in here is 1. So I need sine to be 0, because that makes the imaginary part 0, but I need cosine to be 1. So if you look at that, cosine of theta being 1 implies that theta is equal to like 2 pi k for some k in the integers, right? Theta being 0 implies sine being 0 just says that theta is equal to, say, pi times j for some j in the integers, right? But you put these conditions together, the cosine condition works, right? And we just get theta in the reals such that theta is equal to 2 pi k for some k in the integers. Or a more civilized way to write this, this is just 2 pi z. So the kernel of this mapping is integer multiples of 2 pi. And what's the image of phi? You can also show this. The modulus of theta, phi of theta, is actually equal to cosine squared. Cosine squared theta plus sine squared theta is equal to 1. In other words, phi of theta is an element of what's called S1. This is the unit circle in the complex plane, which forms a multiplicative group, by the way. I mean, here's a proof that it's a multiplicative group. It's the image of a homomorphism, right? So if it's the image of a homomorphism, it's a group. In fact, showing that phi is a homomorphism suffices to prove that the unit circle in the complex plane is a group. Okay? And so in total then, we find this. We find by the first isomorphism theorem, the reals modulo 2 pi z is isomorphic to the circle in the complex plane. And this one's like a lot of fun to think about geometrically. So what it's saying is you're taking the line, right, the real line, and you're identifying points every, 2 pi, right? So like these points are all identified, and they all come up together, and they give you this single point, right? It's a single point on the circle. Or another way you could look at it is you're taking the line, and you're just wrapping it around the circle over and over and over again, and every 2 pi you come back where you started because it's a unit circle. So 2 pi is its circumference. Anyway, I like that example. All right. Another example Oh, well, I hate to get into it at the very end of class, but I don't think I can tolerate notation, Galilean's notation for internal versus external direct products. Like, it's backwards. It's just backwards, guys. Like this, if I say G is equal to G1 plus G2, in my way of thinking, what that should mean is that this is true if and only if G is isomorphic to the crust, the exterior, the Cartesian product of G1 and G2, like that. Maybe I can't get into this right now. But, oh, stink. Can I, well, curses. How to say this nicely. Theorem. No, I can't say that either. I'm very annoyed, guys. I've been searching for the words to express this, and it's exactly backwards in Galilean, and I was trying to follow the book, but I've come to this point where I can't do it. And in terms of that notation, and yet here I am with 2 minutes, so I can't tell you now. Oh well. I guess I'll send an announcement. Nah. Okay, so an example, where was I? 4? 4 was it? So here's one. If I have G, and I'm going to go ahead and start using the new notation if you don't mind. So this means the Cartesian product of G and H. This is not an internal direct product because that's crazy notation for an internal direct product. This is the Cartesian product of G and H, all right? So if I take that, so in other words, this is GH such that G is in G and H is in H, all right? And we multiply them component-wise. So I had used the notation G circle plus H for this previously, right? Hey. Okay, so what happens, guys, if I can define here, for example, pi 1, right? I can define pi 1 from G cross H to G, and I can define pi 2 by G cross H to H as follows. So like pi 1 of GH equals to what? Pi 2 of GH equals to what? My apologies for shifting notation after starting you guys on 1, but I can't in good conscience leave it because it dawns on me he's backwards from everything else under the sun. And it does mean I'm going to be at odds with the book on this notation, but I will try to make you a very clear lexicon of what we're doing. It's not really that complicated. I'm just saying, all I'm really saying, guys, is that this and this are going to get switched in their meaning. The worst thing is, a lot of people use this and this interchangeably. So in that regard, he's not too bad. It's just part of a larger, like I tell my brother about this, and he's like, yeah, well, it doesn't matter, they're isomorphic. I know they're isomorphic. You guys are trying to understand isomorphism, so you need to know when two things are different as point sets. Once you are mature and a math professor, then you can abuse isomorphism. But in the process of learning, you need to know when two sets are different. Algebraists, sorry. So this is G, and this is H. Check this out. What's the kernel of pi 1? What's the kernel of pi 2? Right. Kernel pi 1 is technically it's E, Cartesian product with H. Right? You gotta, I mean, you need to produce an E over here, right? So you gotta put an E in the first thing. And the kernel of pi 1 has to be a subset of the domain, which is the Cartesian product of G and H. So we're kind of stuck there. We have to write something in there. And this one, well, once I did the first one, you guys can do the second one, right? What is it? This is, to be specific, that's E sub G, where this is G cross what? E sub H, right? Are these surjections? Do I hit everything in G, and do I hit everything in H with these maps? Yes, most certainly. So by the first isomorphism theorem, we have that G, the external direct product of G and H by E sub G cross H is isomorphic to G. And, likewise, G external product with H quotient by G, Cartesian product with the identity of H, is isomorphic to H. It's like the G's cancel and the H's cancel. Isn't that neat? This is really just a special case of a more general theorem. The more general theorem is this: if N1 is a normal subgroup of G1 and N2 is a normal subgroup of G2, then check this out. If we take the external direct product of G1 and G2 and we quotient it by the direct product of N1 and N2, all right? That makes sense because that's a subset of that. In fact, you can prove that it's a normal subgroup. In fact, the the Cartesian product of normal subgroups is a normal subgroup. All right? Then guess what this is isomorphic to? You guys want to tell me? I'll start you out. G1 over N1 crossed with what? Yeah, it's true. So there's all kinds of cute results like this that we should go over, and they're all pretty, and that's also pretty easy to prove with the first isomorphism theorem. But anyway, sorry I didn't talk faster today. I wanted to get further, but oh well. Have a good break.